Have you ever wondered how close we've come to losing everything? Imagine a moment when the world teeters on the edge, when the fate of humanity hangs in the balance, only to be spared by the smallest of margins. These near catastrophes aren't just stories from the past. They're real events, shaped by science, fate, and a little bit of luck. From asteroid impacts to nuclear threats, our planet has faced some truly terrifying near ends. But how close were we, really? Join me as we explore 5 moments when the world nearly ended and how we survived against all odds. If you find this journey fascinating, don't forget to like and subscribe so you don't miss the next one. Let's dive in. Long before the age of dinosaurs, before the forests swayed with the breeze or insects buzzed in the air, Earth looked very different. If you were to step into a time machine and visit the Ordovician period, around 485 million years ago, you would not find yourself standing on dry land. Instead, you would be surrounded by vast, shallow seas that covered much of the planet's surface. But these weren't barren waters, far from it. They were rich, bustling ecosystems teeming with life, supporting some of the earliest complex marine life forms that ever existed. The Ordovician seas were full of strange creatures. In the absence of modern-day fish and larger animals, life took on shapes that seemed bizarre by today's standards. You might see brachiopods clinging to the sea floor, filtering water through their tiny shell valves, or trilobites, those hard-shelled, many-legged creatures scuttling along the sandy bottoms. The seas were also home to nautiloids, some as large as a small car, drifting through the water like ghostly torpedoes, propelled by jets of water and guided by clusters of eager tentacles. At this time, evolution was exploring all kinds of life forms. The Ordovician period was one of the most biologically productive periods in Earth's history, marked by what we call the Great Ordovician Biodiversification Event. Over just a few tens of millions of years, the number of different types of marine species more than tripled. Evolutionary experimentation was in full swing. New forms of life emerged, some successful and others not so much, but all playing their part in the grand design of life on Earth. There were creatures that looked like underwater pineapples, sea lilies anchored like organic wind turbines, and even jawless fish with nothing but armor and attitude. These early oceans were rich with nutrients. The conditions were ideal for the types of life that flourished there. The planet was warm, and the continents were slowly drifting. The southern supercontinent, known as Gondwana, was moving southward, but the poles were still relatively warm. Life was abundant in the oceans, and the land was empty of feet. There were no plants, no animals, not even insects to disturb the quiet growth of marine life. The world was, in its own way, thriving. But, as with all things on Earth, stability didn't last forever. Just when it seemed like life in the Ordovician seas had hit its stride, the music stopped. Earth experienced its first known mass extinction event, an event that wiped out over 85% of marine species. The oceans that had been teeming with life suddenly became eerily silent. Ecosystems that had been thriving for millions of years collapsed. Coral reefs, once bustling with activity, withered and died. Whole species that had flourished for eons simply disappeared, leaving only silence in their wake. So, what happened? As is often the case with major extinction events, the causes are complex. Scientists have identified several key factors, with climate change playing a central role. Toward the end of the Ordovician period, Earth entered one of its most severe ice ages. marking a drastic shift in the planet's climate. The warm, stable temperatures that had supported marine life for millions of years began to plummet. This wasn't a slow change either. Geologically speaking, it happened quite quickly. The main culprit behind this cooling trend was the movement of Gondwana. As the supercontinent drifted southward toward the South Pole, it began to accumulate snow and ice. This wasn't just a light dusting. We're talking about full-scale glaciation. As ice sheets spread across the land, the planet's albedo, or reflectivity, increased. This caused more sunlight to be reflected back into space, rather than being absorbed by the Earth. This effect, known as the albedo feedback, set off a chain reaction that caused temperatures to fall even further. The planet, it seemed, was slipping into a self-sustaining winter. At the same time, another major factor contributed to the cooling: a drop in atmospheric carbon dioxide levels. During the Ordovician, volcanic activity was slower than it had been in previous periods. With fewer volcanoes releasing CO2 into the atmosphere, carbon dioxide levels began to drop. Meanwhile, chemical weathering of rocks, particularly as the continents shifted and mountain chains began to rise, caused carbon to be trapped in sediment. This natural process of carbon sequestration further reduced the greenhouse gases that normally helped trap heat in Earth's atmosphere. Together, these factors created a perfect storm for global cooling. As the planet cooled, ice began to accumulate at the poles. Global sea levels began to fall. As water was locked up in glaciers, the vast, shallow seas that had once been home to flourishing marine life began to shrink. Coastal habitats, the rich nurseries of marine life, vanished. The familiar world of warm, shallow waters disappeared, and those species that had adapted to these conditions were left stranded. Life on Earth had never experienced such a drastic climate change. Species that had evolved to thrive in warm, shallow waters now had to contend with freezing temperatures and increasingly hostile conditions. Those that couldn't adapt quickly enough perished. The loss of habitat, the dramatic changes in ocean chemistry, and the global cooling left life on Earth in dire straits. This mass extinction wasn't like other events caused by asteroid impacts or massive volcanic eruptions. It was driven by a combination of slow but relentless changes in Earth's climate changes that built up over tens of millions of years, then accelerated dramatically. But the cooling wasn't the end of the story. After a period of icy desolation, Earth began to warm again. The glaciers melted, sea levels rose, and the environment started to change. However, this shift in temperature brought its own set of problems. The warming of the oceans and the sudden influx of nutrients from the melting glaciers created a new set of stresses on the remaining ecosystems. Ocean circulation patterns were disrupted, and nutrients that had been trapped in the deep oceans were suddenly released into the surface waters. This sudden influx of nutrients could have led to widespread algal blooms, which in turn consumed large amounts of oxygen as they decayed, creating dead zones in the oceans. These low oxygen areas made it impossible for most marine animals to survive. As the oceans warmed, species that had survived the initial cooling faced new pressures. Warming waters disrupted their once stable environments. The increasing levels of nutrients, coupled with the widespread anoxia in the oceans, made life difficult for those creatures that had clung to existence through the initial phase of cooling. Some species managed to survive, but for others, the environmental stress was simply too much. They died off in waves. This second wave of extinction was a harsh reminder of how fragile life can be. But, as with the cooling period, life found a way to persevere. It took millions of years for the ecosystems to recover, but eventually, life did return. The survivors of the Ordovician extinction event formed the foundation for a new wave of biodiversity. Fish with jaws emerged for the first time in the Silurian period. Coral reefs, though they would take time to rebuild, began to thrive once again. The oceans, once emptied of life, began to fill with new possibilities. Despite the eventual recovery, there was a silence that followed the Ordovician extinction, a silence that lingered long after the ecosystems had collapsed. The once vibrant reefs were now quiet. The trilobites, so abundant for millions of years, were gone. The Ordovician seas, so full of life, were now eerily still. And while this was not a silence caused by disease or predators, it was the silence of a world in transition, a world that had been shaped not by the whims of living creatures, but by the slow, relentless changes of a planet reshaping itself. In many ways, the Ordovician extinction was a reset, a moment when life on Earth was forced to begin again. The surviving species would lay the foundation for the ecosystems that would follow. This event was one of the first times that life on Earth was forced to adapt to such extreme conditions, and it would not be the last. The planet had proven that, regardless of how much life had flourished, it could always hit the reset button, wiping out entire ecosystems and starting anew. The Earth has always been the architect of life's story. It reshapes the rules of existence with each passing chapter. For the marine life of the Ordovician, this reshaping was harsh and unforgiving, but it set the stage for the next phase of life on Earth. It was a reminder that Earth's history is not a linear progression, but rather a series of resets, each one creating the conditions for new life to emerge. The Ordovician extinction was not driven by fire from the sky, but by a planet that cooled and then lurched back toward warmth. It was a wake-up call. Earth's own shifts can redraw the rules of life, and survival is never guaranteed. Yet, even under that pressure, life did not end. It adapted, and from the remnants, new possibilities took root. The die-off came in two pulses tied to that climate swing. First, as glaciers spread and sea levels fell, cold and habitat loss crushed shallow water communities. Then, as the ice retreated and seas rose, ocean chemistry changed and a second wave hit the survivors. Each pulse moved like a tide retreating, then returning to erase what was left. The rocks recorded plainly, layers showing vanishing reefs, dwindling trilobites and graptolites, and seafloors turned quiet. Among the many species that were lost, graptolites, colonial organisms that had once flourished in the ancient seas, virtually vanished. These creatures were so abundant that they are now used to help date Ordovician rocks, but their populations were decimated in the extinction event. Brachiopods, some of the most successful filter feeders on the seafloor, were reduced to only a fraction of their former diversity. These creatures had once populated the ocean floors in abundance, but now only a few species remained. Trilobites, those scuttling icons of early marine life, suffered devastating losses. Some lineages disappeared entirely, while others clung to life by the thinnest of threads. The story of their decline is a stark reminder of the fragility of life, even for creatures that had been so dominant in the oceans for hundreds of millions of years. And yet, despite the devastation, not all was lost. A few hardy species survived the chaos, those with broad environmental tolerances or the ability to find refuge in isolated pockets where conditions remained stable. These survivors would go on to repopulate the oceans in the periods that followed, providing the foundation for the next chapter in Earth's long biological story. The Ordovician extinction is sometimes overshadowed by the more dramatic ends of the dinosaurs or the Permian fauna, but in terms of raw numbers, it was one of the most severe extinction events in Earth's history. More than 4 out of every 5 marine species were wiped out during this time, and it all happened without the dramatic impact of a single asteroid or supervolcano. Instead, the cause was the slow, steady grind of shifting continents, changing air, and cooling seas. This quiet force, with no grand explosion or fiery event, upended life on Earth in a way that was as humbling as it was powerful. The silence that followed the extinction is eerie. Earth didn't need a catastrophic flare of destruction to rewrite the rules of life. It simply tilted slightly further from the sun, shifted its continents toward the poles, and let the laws of chemistry and physics do the rest. These quiet forces were powerful enough to wipe out entire ecosystems, leaving no time for those caught in the turmoil to adapt. Yet, even in the face of such sweeping change, life persisted. The seas never became completely silent. Some graptolites clung on. A few trilobites kept crawling. Even after such a massive extinction, life was far from finished. The survivors had a job to do. As Earth settled into its new balance, evolution began once again to explore new possibilities. All the events, the ice, the oxygen loss, the rise and fall of ancient seas, are recorded in the rocks. Layer by layer, fossil by fossil, the story of Earth's first great collapse is waiting to be read. In that story, we don't just find loss, but also resilience. Life had a remarkable ability to adapt, to rebound, and to flourish once more in a world that had been forever transformed. In the long, slow wake of disaster, life found a way to tiptoe forward. After Earth had shivered through its first great extinction, and as the oceans began to warm, something remarkable began to happen. Not suddenly, not loudly, but with a persistence that only evolution could manage, life started to rebuild. The Silurian period, which followed the Ordovician extinction, began around 443 million years ago. Think of it as Earth's recovery room, the calm after the storm. The glaciers that had once covered the poles retreated, and sea levels rose. The shallow seas, which had once been drained and desolate, slowly refilled. As the seas began to stabilize, the survivors, those hardy, adaptable species that had managed to hold on, crept back into the recovering waters. These weren't the flamboyant creatures of the earlier Ordovician seas. They were the underdogs of evolution, but they had one important trait in common. They could endure. Simple brachiopods, those bivalve-like creatures that anchored themselves to rocks and filtered food from the water, made a return. Crinoids, the elegant, feather-armored echinoderms that waved gently in the currents like aquatic ferns, also began to appear again. Trilobites, though their golden age had clearly passed, continued to limp on. The graptolites, which had once been so abundant in the oceans, were now only represented by a few surviving lineages. These survivors, though few in number, were enough to form the foundation of new ecosystems. As the oceans stabilized, these species began to diversify once more, radiating out into new forms of life. The Silurian period was not just a time of recovery, it was also a time of experimentation. With so many species gone, there were vast ecological spaces left vacant. New opportunities arose for innovation and adaptation. Evolution, once again, began to play with new possibilities. One of the most exciting developments of the Silurian was the rise of jawed fish. Fish had already been present in the oceans for millions of years, but they had been simple, jawless varieties, armor-plated creatures that filtered food or scraped algae off rocks. But the evolution of jaws marked a significant shift. Now, these fish could bite, grasp, and chew. Predation had teeth. The earliest jawed fish, such as placoderms, made their debut in the Silurian seas. These were bulky, heavily armored creatures, their heads and shoulders covered in bony plates. They weren't just swimming and filtering their way through the waters. They were the tanks of the ancient oceans. Their arrival marked a turning point in marine ecosystems, as the first complex predator-prey dynamics began to emerge. It was no longer enough for an organism to simply be armored or slow-moving. If you couldn't swim faster, hide better, or adapt in some clever way, you became prey. But jawed fish didn't stop there. A new group, known as acanthodians, often called spiny sharks, also began to emerge. These fish were sleek swimmers, lighter in armor and bristling with spines. They were early prototypes of the bony and cartilaginous fish that would eventually evolve into the sharks, rays, and bony fish we know today. This marked a monumental shift in marine life, as the oceans became a more dangerous place. However, the impact of the Silurian period wasn't confined to the seas. Life also began to creep onto land, though not yet in the form of animals. The first terrestrial colonizers were plants. Simple, spore-producing species, such as Cooksonia, began to appear along moist shorelines and riverbanks. They had no leaves, no roots, and certainly no flowers. But they had something just as important: vascular tissue. This allowed them to move water and nutrients through their bodies, which meant they could grow taller and survive in drier environments than their algal ancestors. This might not seem like much, a few centimeters of mossy green pushing above the mud, but it was the beginning of a revolution. These early plants began to stabilize the soil, influence weathering, and even impact atmospheric carbon dioxide levels. In time, their descendants would go on to shape entire continents. But for now, they were simply the first hints of green in a world that had long been dominated by blue and gray. Meanwhile, the Silurian seas became more complex. Coral reefs began to return, though not the modern corals we are familiar with today. These were ancient coral builders, known as tabulate and rugose corals. These organisms, while different from modern reef builders, still had a knack for constructing intricate structures. These reefs provided shelter for smaller creatures and created new ecological niches. The return of coral reefs added structure to the recovering marine ecosystems. The Silurian period also saw the return of eurypterids, or sea scorpions. These formidable predators, with their spiked limbs and powerful swimming paddles, grew to some of the largest sizes ever recorded for arthropods, reaching lengths of over 2 meters. While they were fearsome in appearance, they were a sign of the revival of life, proof that Earth's ecosystems were not only returning, they were branching into new and spectacular forms. Mass extinctions often lead to bursts of innovation, and the Silurian was no exception. After the devastation of the Ordovician extinction, life began to adapt and evolve in ways that were previously unimaginable. New species arose to fill the gaps left by those that had perished, and the stage was set for the next great chapter in Earth's history. When dominant species vanish, they leave behind open real estate habitats with no tenants, food chains, missing key links, and ecological roles unfilled. In the aftermath of extinction, the survivors often find themselves in a world without competition, without predators, and without the established rules that once governed the planet. And in that open space, evolution gets to work. experimenting with new ideas, trying out body plans, feeding strategies, and methods of locomotion that were previously unexplored. What might have once seemed too risky or unnecessary for survival now becomes the key to it. In a stable environment, change happens slowly, cautiously, and predictably. But in a disrupted world, with so many vacant ecological niches, change becomes bold and experimental. Evolution throws all sorts of options at the wall to see what sticks. The Silurian period offers a gentle example of this principle. It wasn't a dramatic, immediate explosion of life, but rather a steady, quieter rise of new possibilities. The recovery was not smooth or instantaneous. Ecosystems take time to rebuild, and biodiversity takes millions of years to return to pre-extinction levels. In some cases, groups never fully recovered. Others were permanently altered. Yet, taken as a whole, the biosphere proved astonishingly resilient. This resilience is a key lesson from Earth's history. Extinction and innovation are often two sides of the same coin. One clears the canvas, the other picks up the brush. The first great mass extinction of the Ordovician period was not the end of the story. It was simply the end of a chapter. What followed, though quieter, was no less significant. The Silurian world was one of rebuilding, rethinking, and reinvention. The recovery after such a catastrophic event is comforting in a way, showing that no matter how many times life stumbles, it always seems to find a way to stand back up. It adapts, it reimagines itself, and sometimes, from the ruins of catastrophe, it builds something entirely new. The oceans of the Silurian may not have been as glamorous as those of the later Mesozoic, or as strange as those of the Cambrian, but they hold a special place in Earth's history. They were the waters that cradled recovery. They nurtured the early days of jawed fish and the first green shoots of terrestrial life, and through their quiet transformations, they whispered that life, fragile though it may be, is remarkably persistent. As Earth moved into the Devonian period, starting around 419 million years ago, the planet seemed ready to become the stage for a planetary success story. The continents were beginning to take on familiar shapes, though still shuffled into unfamiliar configurations. Massive inland seas sparkled under a warm sun, shallow and rich with nutrients. Green patches began to emerge along the coastlines, not just small mossy mats, but the first true forests, built from plants that had finally cracked the code of vertical growth. These early forests weren't the kind of dense, leafy woodlands you might find on a modern hike. Instead, they were dominated by towering lycophytes, horsetails, and primitive ferns, plants with thick bark and very few leaves. Some had the look of shaggy poles, with trunks but no flair. Still, they were monumental. These plants had learned how to grow tall, with roots that reached deep into the soil, stabilizing it and preventing erosion. Branches stretched skyward in search of the sun, and with this vertical growth came an unexpected consequence, a change in the atmosphere itself. More plants meant more photosynthesis, and more photosynthesis meant more oxygen in the air. This shift in the atmosphere was crucial. The air was becoming breathable for the right kinds of lungs. It wouldn't be long before creatures began to venture onto land. The first insects, small but significant, were already skittering through the damp leaf litter, taking advantage of the newly green world. Millipede-like creatures traced paths between roots, and primitive wingless insects fed on decaying plant matter. These were small steps, but they signaled the beginning of a quiet revolution. Life wasn't just surviving on land, It was adapting, diversifying, and learning to thrive. Meanwhile, in the oceans, things were even more spectacular. The Devonian seas were crowded with fish, and not just any fish. This was the age when fish got weird, wonderful, and downright dramatic. Jawless fish were still around, but they were quickly being outshined by their newer, flashier cousins. Placoderms, heavily armored fish with powerful jaws, ruled the seas like underwater gladiators. Some, like the massive Dunkleosteus, were apex predators with bone-crushing bites, and they had the fashion sense of medieval knights, with bony armor covering their heads and bodies. Ray-finned fish and lobe-finned fish also emerged during this period. While ray-finned fish would go on to dominate the world's oceans, lakes, and rivers, it was the lobe-finned fish with their muscular, sturdy fins that would eventually give rise to the first tetrapods. These early fish were tinkering with limbs, experimenting with ways to move that might work on land as well as in water. Evolution was laying the groundwork for life to transition from water to land. Reefs were booming too. The Devonian period was one of the great reef-building eras in Earth's history. Massive reef structures, many stretching hundreds of kilometers, were constructed not by modern corals, but by stromatoporoids and tabulate corals, ancient reef builders that had a knack for construction. These reef ecosystems were rich, diverse, and teeming with life. They were the rainforests of the sea long before there were any rainforests on land. The oceans were flourishing, and the planet seemed to be on the verge of a golden age, a time of expansion and opportunity. But golden ages, as history often teaches, can be fragile. Beneath all this growth and innovation, a slow-motion catastrophe was beginning to stir. Unlike some mass extinctions, which strike with the sudden force of an asteroid impact or a volcanic eruption, the Devonian extinction was more gradual, unfolding over roughly 20 million years. This drawn-out affair involved a complex pattern of ecological stress, extinction pulses, partial recoveries, and renewed collapse. Scientists refer to this as a series of pulse extinctions. These were periods when extinction rates spiked sharply, followed by quieter intervals where life tried to regroup, only to be knocked down again. At least 5 major extinction pulses are recognized within this stretch, each one taking a toll on different groups of organisms. The causes of this long decline are still being pieced together, but several suspects stand out. One leading theory points to the forests themselves. More specifically, the way plants were beginning to reshape Earth's surface and atmosphere. As roots dug into rocks and soils, they increased the rate of chemical weathering, which drew down atmospheric carbon dioxide, gradually cooling the planet. As plants stabilized soils, however, this also meant that when heavy rains came, massive amounts of nutrients were washed into the seas. This sudden influx of nutrients likely fueled massive algal blooms in coastal waters. These blooms, as they decayed, consumed vast amounts of oxygen, creating dead zones in the oceans. Oxygen levels plummeted, especially in deeper waters, and marine life began to suffer. These expanding dead zones may have been one of the primary causes of the Devonian extinction. Entire habitats became uninhabitable, suffocating the reefs and the creatures that depended on them. The reefs that had flourished earlier in the Devonian virtually vanished, and true reef building would not return at the same scale for another 100 million years. Fish, too, were hard hit. Many placoderms went extinct, including some of the largest and most fearsome predators of the time. Lobe-finned fish and early tetrapods suffered significant losses, especially near the end of the Devonian. The shallow coastal environments they favored became increasingly unstable, with fluctuating temperatures, oxygen levels, and salinity, making survival a game of chance. Despite the drawn-out nature of the crisis, the long-term effect was clear. Biodiversity dropped significantly. Whole groups of animals were permanently reduced. The complex ecosystems that had taken millions of years to develop were thinned out, simplified, and left in a state of flux. But, as always, some lineages managed to hang on. Small, generalist species had an advantage. Creatures that could tolerate low oxygen levels, fluctuating environments, or limited food supplies found ways to persist. Among these survivors were the ancestors of future amphibians, clinging to existence in freshwater margins, and the early arthropods that skittered through detritus both above and below the waterline. The hallmark of life on Earth is survival through adaptability. Even as crises reshaped the planet, life found ways to adjust, recover, and rebuild. The Devonian period, though full of upheaval, set the stage for what followed, proving that resilience can be creative as well as persistent. In that new landscape, the survivors were poised to drive the next wave of evolution. What makes the Devonian extinction especially important is how it redirected vertebrate history. By thinning out the dominant marine predators, it opened space room for new adaptations and new kinds of creatures to rise. It didn't instantly produce something better, but it did clear the field for fresh experiments. With old pressures eased, evolution had room to try again, and that freedom shaped the long path life would take afterward. There's something eerie about a mass extinction that unfolds over time. It doesn't strike suddenly with cataclysmic force. Instead, it unfolds like a long illness. The symptoms come and go, sometimes deceptively mild, other times alarming, until one day you realize that the system has changed entirely. The Devonian extinction didn't end with a bang, but with a drawn-out wheezing gasp. Yet, within this quiet unraveling, a few strange and hopeful things survived. A stubborn little group of lobe-finned fish, for instance, with bones sturdy enough to lift themselves onto muddy banks. Over millions of years, their descendants would evolve to walk fully on land, breathe air through lungs, and look around at a world that had been shaken but was still open for exploration. The Devonian boom, full of promise and potential, ended in a slow bust. But like every fall in Earth's history, it carried with it the seeds of something new. The forests that contributed to the crisis would go on to sculpt entire ecosystems, and the tetrapods that clung to existence would eventually walk the Earth. Evolution, undeterred by setbacks, kept going one careful step at a time. It's easy to think of trees as gentle giants, stoic, leafy guardians of the land, offering shade, shelter, and the soft rustle of reassurance on a breezy day. But during the Devonian period, trees were new to the world, and like many newcomers, they caused a bit of chaos. In fact, if you were a trilobite trying to enjoy your twilight years on the seafloor, trees might have seemed less like wise old sages and more like clumsy environmental saboteurs. Because, as it turns out, the rise of forests may have triggered one of the most insidious mass extinctions in Earth's history, not through fire or brute force, but through roots, rocks, and a slow, silent transformation of the world's oceans. Let's rewind to the Middle and Late Devonian, roughly 390 to 360 million years ago. Life on land was still a fledgling experiment. Mosses and liverworts had already crept across damp soils, but now vascular plants were making their big move. These new contenders weren't content to sprawl low to the ground. They were reaching upward towards sunlight, above the competition, and they had the tools to do it. Tough woody tissues for support, true roots for anchorage and internal plumbing to move water and nutrients. Among the first true trees was Archaeopteris, a tall, fern-like plant with woody trunks and leafy branches. It could grow over 20 meters high, forming dense stands that resembled forests, both in structure and scale. These weren't forests in the modern sense, no birds nesting, no squirrels darting between branches, but they were forests nonetheless, and they represented a revolution in terrestrial life. Now, here's where things get interesting. Those roots digging deep into Devonian soils began to change the planet. They broke up rock as they grew, a process called biological weathering. As roots pushed into cracks and pores, they released acids that helped dissolve minerals. This breakdown of rock wasn't just good for the plants, providing access to nutrients like phosphorus and calcium. It also had profound effects on the climate and the oceans. When rocks weather, they bind up atmospheric carbon dioxide in a series of chemical reactions. Rainwater, slightly acidic due to dissolved CO2, reacts with silicate minerals in rocks to form bicarbonates. These eventually wash into rivers, flow to the ocean, and settle out as carbonates on the seafloor. Over long periods, this process can pull vast amounts of CO2 from the atmosphere, reducing the greenhouse effect and cooling the planet. In the Devonian, with roots accelerating this weathering process across entire continents, it's likely that carbon dioxide levels dropped significantly. That cooling effect alone would have been enough to disrupt ecosystems. But the real mischief came from what followed: nutrient runoff. As soils weathered and forests expanded, more nutrients, particularly phosphorus and nitrogen, were flushed into rivers and carried to the sea. And here's where the ocean, usually a fan of balance, began to tip. When large quantities of nutrients enter marine environments, they often trigger blooms of algae and plankton. At first, this can seem like a good thing: more food for filter feeders, more photosynthesis. But when those blooms die off, they sink to the bottom and decompose. The decomposition process consumes oxygen. In shallow seas and coastal areas, this can quickly lead to hypoxia, low oxygen conditions, or worse, full-blown anoxia, where oxygen is entirely absent. In the Devonian, this process may have spread far and wide. The fossil record shows clear signs of anoxic black shells forming in various parts of the world's oceans during this time. These rocks, dark and organic rich, are laid down in environments where decay outpaces oxygen renewal. They tell the story of a suffocating sea. Marine life, already dealing with fluctuations in temperature and sea level, now had to face the loss of breathable water. Reefs collapsed, filter feeders vanished. Even mobile animals like fish couldn't outrun the spreading dead zones. It was a slow-motion ecological disaster, and trees, of all things, may have helped write the script. Of course, the trees didn't mean to. They were just doing their tree thing, growing, rooting, breathing, photosynthesizing. There were no sinister plots hatched in the branches of Archaeopteris, no whispered plans for oceanic upheaval. But when viewed through the lens of Earth systems, their arrival was nothing short of revolutionary. By greening the continents, they set in motion a cascade of changes that altered the climate, chemistry, and biology across the globe. In a way, it's the earliest known example of what we might call unintended ecological consequences. A new form of life emerges, reshapes its surroundings, and unwittingly destabilizes the very systems that support it. It's an ancient pattern, and a familiar one. There's a certain speculative humor in all of this. Imagine the conversation in a Devonian reef. "Hey, have you noticed the water's getting a bit murky?" "Yeah, and the oxygen's kind of low. Must be the weather." "Nope, it's the trees." "The what?" It's almost comical that the quiet, leafy rise of terrestrial plants could outmatch the armored fish and coral reefs with its ecological impact. But that's the thing about big changes. They often come not with a bang, but with a root. Interestingly, the effects weren't confined to the seas. The Devonian forests may have also influenced fire regimes. More plant matter on land meant more potential fuel, and with increased atmospheric oxygen, wildfires likely became more common. Charcoal deposits from the period suggest that fire had entered the scene in a serious way. The Earth was becoming more dynamic, more interconnected. Land, sea, atmosphere, all woven together in a feedback loop of cause and consequence. The Devonian, then, becomes a test case not for malice, but for complexity. It reminds us that ecosystems are sensitive and that life, even when it flourishes, can tip the balance of the world in unpredictable ways. Trees didn't destroy the oceans out of spite. They just changed the rules of the game, and the rest of the biosphere struggled to keep up. Yet, even with the collapse of reef systems, the loss of marine species, and the spread of anoxic waters, life found ways to adapt. Some organisms moved into deeper, more stable waters. Others evolved strategies to cope with low oxygen. On land, plants continued to diversify, their roots reaching deeper, their forms becoming more elaborate. Insects followed, evolving new behaviors and body plans. The tetrapods, those early four-limbed vertebrates, edged closer to a terrestrial future. It's a fascinating irony. The very forests that helped trigger a marine extinction also created new opportunities for life on land. In the Devonian, crisis and innovation walked hand in hand. What was lost in the sea was, in a strange way, compensated for in the woods. So, were trees the villains of this chapter? Probably not. But they do serve as a reminder that even the most peaceful-seeming organisms can change the world in profound and unpredictable ways. They are the original geoengineers, the first terraformers, the quiet revolutionaries who didn't just survive on Earth, but remade it. And in doing so, they taught a valuable lesson. The world is never static. Even when life seems rooted in place, it can set everything in motion. In the great Devonian drama of life, the fish were undoubtedly the stars, glittering, armored, jawed, and hungry. But like many celebrity tales, their golden age came with a twist. Some rose, others fell, and a few awkward creatures shuffled their fins onto dry land and became the pioneers of a new world entirely. When the Devonian extinction pulses finally began to ease, the stage was eerily quiet. Whole ecosystems had unraveled. Reefs were gone. Oxygen levels in the seas had dropped, and many of the once dominant creatures had vanished. But from the silence that followed, life began to adapt. The survivors would lay the groundwork for the ecosystems of the future. What seemed like a catastrophe, a slow-motion unraveling, was, in reality, just another chapter in Earth's ongoing evolution. Among the most notable casualties of the Devonian extinction were the placoderms, those jawed armored fish that had swaggered through the seas like aquatic tanks. With their bony helmets and crushing jaws, they had seemed invincible. But as environmental conditions deteriorated and marine ecosystems collapsed, their dominance crumbled. The reasons for their decline are still being pieced together, but like most extinction stories, it wasn't a single culprit. Their large size and specialized lifestyles, may have made them less adaptable to sudden changes in oxygen levels, temperature, and habitat. When food webs and dead zones spread across the oceans, the placoderms simply couldn't keep up. By the end of the Devonian, they were gone extinct. Despite their impressive armor, their departure left an ecological vacuum, an empty space in the food chain. And into that void swam the quiet contenders, the ray-finned fish. Unlike their heavily armored predecessors, ray-finned fish were lighter, more flexible, and far more adaptable. Their fins, supported by bony spines rather than fleshy lobes, gave them agility and speed. They could dart through changing environments, adjust their diets, and exploit niches that the bulkier placoderms had ignored. At first, they didn't look like much. Small, modest, unassuming, but they were the blueprint for what would become the most diverse group of vertebrates in Earth's history. From humble beginnings, ray-finned fish would go on to fill rivers, lakes, and oceans with a dizzying array of forms: shimmering schools of sardines, lurking anglerfish with luminous lures, sleek swordfish, and graceful seahorses. But back in the late Devonian, their advantage was simple. They could survive, and survive they did, quickly becoming the dominant group in marine ecosystems. Also clinging to life were a group of lobe-finned fish. Though not as nimble as their ray-finned cousins, they had something special: bones in their fins. These bones provided a kind of internal scaffolding that, in time, would evolve into limbs. One lineage of lobe-finned fish, for reasons that can only be described as ambitious, began to explore the murky margins between water and land. These creatures, the early tetrapods, were not quite fish and not quite amphibians. They had lungs as well as gills. Their fins were fleshy and equipped with rudimentary digits. They could prop themselves up in the shallows, wiggle through mudflats, and possibly make short excursions onto land to hunt or escape predators. It wasn't glamorous, no one was sprinting across sunlit meadows, but it was a beginning. One small, squelchy step toward life on land. Amphibians, or at least their ancestors, also emerged during this uncertain time. They were closely related to the early tetrapods, and like them, they straddled the divide between water and air. These creatures likely laid their eggs in water, breathed through skin or simple lungs, and navigated a world in flux, a patchwork of swamps, rivers, and damp forests. Their survival strategy was one of flexibility. They didn't need pristine coral reefs or open oceans. They could eke out a living in brackish pools, shallow streams, and freshwater deltas. While the great marine predators vanished, these smaller, adaptable vertebrates quietly endured. The late Devonian extinction had created a classic evolutionary bottleneck. Many lineages disappeared, leaving only a few survivors to repopulate the world. But as history has shown time and again, such bottlenecks can be powerful engines of innovation. When diversity is low and competition is reduced, evolution gets creative. The survivors of the Devonian weren't necessarily the flashiest or fiercest. They were the most versatile. They had broad diets, wide tolerances for temperature and oxygen, and life cycles that could ride out environmental uncertainty. These were the traits that mattered when the world was unstable. Once the worst of the extinction was over, life began to expand again, gingerly at first, then with more confidence. The Carboniferous period dawned, bringing with it lush, swampy landscapes and an explosion of biodiversity. Plants blanketed the land in dense forests, and oxygen levels in the atmosphere soared. Giant insects buzzed through the air, and amphibians flourished in the wetlands. The vertebrates that had survived the Devonian bottleneck now diversified into an astonishing array of forms. But even as they branched out, the mark of the extinction remained. It had filtered out entire evolutionary pathways. It had left a legacy of survival and simplification. From that lean, stripped-down starting point, new complexity would slowly emerge. The Devonian extinction didn't just wipe the slate clean, it reshaped the very architecture of vertebrate evolution. Without it, placoderms might still dominate the seas, and the awkward little tetrapods might never have had the chance to crawl ashore. Instead, the extinction created space. It granted opportunity, and those who took it would go on to reshape the planet in ways the armored giants of the Devonian could never have imagined. It's tempting to root for the underdog in these stories, the scrawny ray-finned fish, the flopping tetrapods, the amphibians quietly clinging to pond margins. And maybe that's fair. After all, from those uncertain survivors came the whales, the birds, the reptiles, the mammals, everything with a spine that ever leapt, walked, soared, or sang owes something to the creatures that weathered the Devonian's slow unraveling. They were the ones who didn't give up, who swam a little further, climbed a little higher, breathed a little deeper, and in doing so, they carried life through one of its darkest hours and into a future filled with promise. Looking back, we see that the Devonian extinction wasn't just a catastrophe. It was a turning point, a necessary disruption that, although it caused great upheaval, ultimately allowed new life forms to flourish. The survivors of that era, though seemingly unremarkable, became the progenitors of nearly every major branch of life that would follow. The late Devonian extinction, with its gradual, almost imperceptible pace, created a world that was primed for evolution. It was a crucible, a trial by fire that ultimately forged the path to life on land. And in this long, winding process, the survivors of the extinction didn't just endure, they adapted. They evolved new strategies for survival, exploring new territories and new possibilities. From the watery depths to the muddy shores, from the swamps to the skies, these survivors laid the groundwork for the explosion of life that would define the Carboniferous and beyond. The extinction, in its drawn-out, slow-motion devastation, didn't just mark the end of one world. It marked the beginning of another one, in which life would, once again, rise from the ashes, not with a roar, but with a soft, persistent push toward the future. The Devonian extinction, as we now see, wasn't just a story of loss, but of opportunity. The extinction gave way to creativity, to adaptability, and to life finding new ways to thrive. The legacy of those survivors, those small, humble creatures, would echo through the eons, shaping the future of life on Earth in ways that even the mighty placoderms could not have imagined. In their fall, the course of evolution shifted, and the path to the world we know today was set into motion. The survivors of the Devonian extinction were not just the underdogs, they were the architects of the future. Roughly 252 million years ago, the world faced its darkest hour. It wasn't a single bad day or a short run of storms. It was a full planetary crisis, an extinction so severe it's known as the Great Dying. That name is not poetry. It is the simplest label for the worst biological disaster in Earth's history. This was not a minor correction in evolution. It was a near erasure. More than 90% of marine species disappeared, and about 70% of land-dwelling vertebrates were lost. Whole ecosystems failed. Coral reefs collapsed. Forests thinned, and then vanished from large regions. Even insects, usually tough survivors, suffered unusual, heavy losses. The tree of life was not just pruned, The trunk was chopped back to a few stubborn shoots. The setup matters. In the late Permian, Earth's landmasses were fused into one supercontinent, Pangaea. It stretched from pole to pole and was wrapped by the Panthalassic Ocean. That geography pushed climate toward extremes. Interiors of the continent were dry and hot by day, cold by night, with large deserts and erratic rain. Coastal belts and basins held more moisture, but many habitats were already stressed before the main blow arrived. The main blow was the Siberian Traps. In what is now Siberia, one of the largest volcanic events on record, built up layer after layer of basalt. Over roughly 1 million years, enough lava erupted to bury an area the size of modern Australia under sheets kilometers thick. The lava itself was destructive locally, but the gases were the global problem. The eruptions pumped huge amounts of carbon dioxide and sulfur dioxide into the air, 2 trapped heat, and drove a sharp warming trend. This was not a mild rise. Ocean surface temperatures climbed by several degrees. The deep ocean warmed, circulation slowed, and oxygen delivery to depth faltered. So too made sulfuric acid in the atmosphere. Acid rain fell on forests and soils, stripping nutrients and stressing freshwater systems. Warming set off feedbacks. As temperatures rose, methane trapped in seafloor clathrates may have been released. Methane is a stronger greenhouse gas than CO2 over short timescales. A pulse of methane would have pushed temperatures higher still, helping turn warming into a runaway. On land, heat waves grew longer. In the seas, the same warmth that slowed mixing also changed the chemistry. Oxygen levels dropped. Large regions became anoxic water with little or no oxygen. In those waters, many animals could not breathe. Shell-building organisms, which had been successful for hundreds of millions of years, crashed. Coral frameworks disintegrated. Trilobites, veterans of earlier crises, disappeared for good. Anoxia often travels with another threat. In low oxygen, nutrient-rich settings, some microbes thrive and produce hydrogen sulfide, a toxic gas with a rotten egg smell. If that gas builds up and reaches the surface, it can poison shallow seas and coasts. If enough escapes into the air, it can damage the ozone layer. A thinner ozone layer lets more ultraviolet radiation reach the surface, adding stress to land, plants, and plankton. Evidence from rocks points to intervals of black, organic-rich shales laid down in anoxic waters, and to chemical signs of unusual sulfur cycling. Together they map a world ocean that was, at times, suffocating. The land record tells a matching story. Forests declined. There is a coal gap in early Triassic rocks. Few thick coal beds, meaning fewer extensive peat-forming swamps. Spores and pollen shift toward hardy types that tolerate dryness and disturbance. Some layers show spikes in fungal remains, consistent with widespread decay of dead plant matter after forest die-off. Rivers changed course more often as routes that once stabilized floodplains were lost. Sediment loads rose. Freshwater habitats flickered between flood and drought. Amphibians and many reptiles, already heat-stressed, faced scarce shelter and unstable food webs. Large herbivores and their predators vanished from many regions. The timing was not a single instant. The extinction unfolded in pulses over tens to hundreds of thousands of years. There were lulls and partial recoveries, then renewed losses, but the direction was clear. By the peak, diversity had fallen to a fraction of its former value. When the worst passed, the biosphere was quiet, yet it was not empty. Some small burrowers, animals that lived in the ground where temperatures and humidity were steadier, made it through. In the oceans, a few bivalves, gastropods, and opportunistic ammonoids survived in refuges where oxygen still reached the seafloor. Microbial mats spread across tidal flats that had once held seagrasses and complex bottom faunas. Life collapsed into simple, robust forms that could tolerate heat, low oxygen, and poor food chains. Among the land survivors, Lystrosaurus stands out. This pig-sized, tusked herbivore with a beaked mouth appears in high numbers in early Triassic rocks across what are now Africa, India, and Antarctica. It was not elegant, but it was tough. A simple body plan, broad diet, and likely burrowing or semi-burrowing habits fit the new world. In many places, Lystrosaurus makes up a huge share of the vertebrate fossils right after the boundary, a sign of how skewed communities became. Paleontologists call such dominant, hardy survivors disaster taxa. They are not the peak of complexity. They are the bridge between collapse and recovery. Why did Pangaea make things worse? A single supercontinent has long coastlines, but huge interiors. Without many small seas to moderate climate, heat builds inland. Monsoons can be intense yet seasonal, leaving long, dry intervals. With forests gone, bare soils reflect more heat by day, but also lose moisture faster, making droughts worse. Dust increases. That dust can carry iron and phosphorus to the oceans, fertilizing surface waters and aiding blooms that later drive anoxia below. Land, air, and sea formed a linked stress system. Warming, acid rain, nutrient runoff, ocean stagnation, anoxia, toxic gases, ozone damage, and more warming. The Great Dying reset evolutionary space. With so many dominant groups gone, new lineages could expand. Early archosaurs, the broader group that later gave rise to crocodiles, pterosaurs, dinosaurs, and ultimately birds, found open ground. Synapsids, the group that includes the ancestors of mammals, passed through a narrow bottleneck and then diversified into small, active forms with higher metabolism. In the seas, simple bivalves and ammonoids radiated first, followed by new reef builders much later. True coral reef ecosystems took millions of years to return. For a long stretch of the early Triassic, communities were low in diversity, dominated by few species, and prone to boom-bust swings. Recovery was not quick. Estimates suggest 5–10 million years for basic ecosystem structure to re-establish, and far longer for full reef complexity. The lesson is about connections and thresholds. A volcanic province in one region can heat the globe, change rainfall, acidify soils, and strip oxygen from the sea. Feedbacks: methane release, dust fertilization, microbial blooms can turn stress into spiral. Once certain limits are crossed, systems do not glide back to normal. They reorganize around simpler, tougher forms. Nearly all life was squeezed into a handful of lineages, not by an asteroid, but by lava, gas, and time. Even so, the record shows continuity. Genes carried through small bodies in burrows and shallow bays. Breath moved from gill to lung and back again in the few species that could shift with the water. After the worst heat, some climates cooled a little. Plants returned first as scrub and open woodlands, then as patchy forests. Rivers stabilized. On land, archosaurs took advantage of the open niches. In the water, new predators learned the rebuilt rules of the sea. There is no sign of triumph in these rocks, only the steady marks of survival and the slow rebuilding of function. There is hot, and then there is Permian hot, the kind of heat that does more than make you sweat. It melts landscapes, turns rain to acid, slows the ocean's breath, and rewrites the chemistry that life depends on. In that heat, the planet showed how tightly its systems are bound together and how quickly they can tip when pushed. The page did not turn in a single day. It turned in layers of ash and shale, in gaps where coal should be, in tracks of a tusked grazer crossing a bare floodplain, and in shells thin enough to tell you how little oxygen the water held. Picture a world where the sky darkens with ash, the oceans simmer with heat, and the ground opens in fiery cracks. That is close to what Earth looked like at the peak of the Siberian Traps eruptions. The Traps are not a single volcano, but a vast province of basalt in what is now Russia. During the late Permian, they were not quiet rocks. They were wide fountains of lava, pushing columns of gas and ash into the sky for hundreds of thousands of years. The name Traps comes from the step-like layers of basalt left by one flow after another. The pattern may look like stairs in stone, but the impact was anything but measured. This was flood basalt volcanism on a continental scale, covering more than 7 million square kilometers, more than twice the size of India, in thick sheets of molten rock. The danger did not end with the lava. The magma and the hot intrusions burned through carbon-rich sediments, releasing carbon dioxide in vast amounts. Contact metamorphism baked coal beds and organic shales, driving off more CO2 and other gases. The result was a sharp surge in greenhouse forcing. Global temperatures rose by many degrees. Summers grew longer and hotter. Winters stayed warm. Heat soaked into the upper ocean. Because warm water holds less oxygen, the chemistry of the seas began to shift in the worst way possible for marine life. As the surface warmed and density contrasts changed, ocean circulation slowed. The deep sea depends on overturning currents to bring down oxygen from above. With mixing reduced, bottom waters lost their breath. Anoxic zones spread across shelves and into basins. In these oxygen-starved settings, many familiar animals could not live. Shell builders struggled to form and maintain carbonate skeletons in waters that were both warm and chemically unstable. Reef frameworks collapsed. Communities that once filtered, grazed, and hunted around those reefs vanished. Low oxygen also favors different microbes. In the late Permian seas, purple sulfur bacteria appear to have flourished in places. They use hydrogen sulfide rather than oxygen in their metabolism. That gas smells like rotten eggs at small levels, but becomes deadly at higher concentrations. Geological markers, black, organic-rich shales, sulfur isotope shifts, pigments preserved in sediments line up with episodes when hydrogen sulfide likely built up in bottom waters and sometimes reached the surface. In calm weather and along certain coasts, poisonous clouds could have drifted ashore. In the upper atmosphere, hydrogen sulfide and its products can thin the ozone layer. With less ozone, more ultraviolet radiation reaches land and sea surfaces, stressing plants, plankton, and animals already near their limits. Sulfur dioxide from the eruptions added another layer of harm. In the air, it formed sulfuric acid droplets that cooled the surface for short spells and returned as acid rain. Soils were leached. Lakes and streams turned acidic. Forests that had anchored floodplains and fed peat swamps were stripped back. After the boundary, there is a clear coal gap in many regions. Few thick coal seams, meaning peat-forming forests were rare for a time. Without those roots, riverbanks failed more easily. Rivers braided and wandered, dumping loads of sand and silt into lowlands and onto shelves. That sediment carried nutrients like iron and phosphorus into the sea, which fed surface blooms that, when they died, drove still more oxygen loss below. The land, the air, and the water locked together into a harsh feedback loop. The extinction unfolded as a cascade rather than a single blow. Volcanism drove warming. Warming slowed ocean mixing and lowered oxygen. Anoxia favored sulfide-producing microbes. Sulfide and aerosols damaged ozone, vegetation, and food webs. Vegetation loss sent more dust and nutrients to the sea, which fed new blooms that deepened anoxia. Each step pushed the next. Species tried to track their moving ranges, shift diets, or change habits, but the rate and breadth of change overwhelmed most of them. Coral reefs disintegrated. Trilobites, long-lasting veterans of earlier crises, ended for good. Many armored fishes and shelled cephalopods disappeared. On land, amphibians with moisture-sensitive skin were hit hard by heat and drying. Reptiles did a bit better, but many lineages still fell. The survivors were few. Amid this, one land animal became a symbol of persistence: Lystrosaurus. It was a pig-sized, tusked synapsid, neither mammal nor reptile, but a cousin on the mammal side of the tree. Its body was barrel-shaped. Its legs were short and sturdy. Its face was broad, with a beak-like mouth for cropping tough plants, and small tusks rooted in the upper jaw. It likely had a simple, efficient lifestyle. Dig or shelter, eat hardy vegetation, tolerate heat and dryness better than many rivals. In early Triassic rocks, Lystrosaurus fossils are common across what are now Africa, India, and Antarctica. In some beds, they dominate the vertebrate remains. Paleontologists call such hardy, abundant forms disaster taxa. They fill landscapes during recovery, when ecosystems are simple and unstable. Marine survivors had a similar profile. Bivalves and gastropods with broad tolerances persisted where oxygen still reached the sea floor or in shallow, well-mixed bays. A few ammonoids hung on and later diversified. Microbial mats covered flats and lagoons that had once held complex communities. For a time, food webs were short, with few species and big swings in numbers. True coral reefs did not return for millions of years. The early Triassic is marked by repeated setbacks, warming spikes, renewed anoxia, brief rebounds, before more lasting stability returned. Pangaea's geography made recovery harder. With a single giant continent, inland climate swung between drought and flood. Monsoon belts shifted. Coastlines were long, but often backed by deserts. Without many small seas and varied shelves, there were fewer mild refuges. Yet, even with those limits, the slow climb began. As volcanic output waned and weathering drew down some of the excess CO2, temperatures eased a little. Hardy plants recolonized river corridors. Soils formed. Insects and small vertebrates spread with the green. Rivers stabilized. On land, archosaur relatives expanded into vacant roles. In the oceans, simple communities grew step by step toward complexity. The power of the Siberian traps lies in the way they show connection. A mantle plume or deep rift feeds eruptions. The eruptions change air chemistry. Air chemistry shifts climate. Climate alters rainfall, fire, and weathering. Weathering moves nutrients and minerals to the sea. The sea loses oxygen. Microbes change their mix. Gases rise and damage the ozone. UV increases and harms life. The loop tightens. No asteroid was needed. Fire, gas, and time did the work. The end state, for a while, was a planet that seemed to be learning to live again. The skies cleared. The lava cooled to stone. The seas, though still warm and often stressed, began to circulate a bit more. Into that space stepped the few lineages that had made it through. Their traits, generalist diets, tolerance of heat and low oxygen, simple growth and breeding cycles, were the right tools for rebuilding. From them, in the Triassic, came the first strong waves of new forms. Early archosaurs that would give rise to crocodiles, pterosaurs, and dinosaurs. Small synapsids on the path to true mammals. Ammonoids and bivalves filling empty seafloors. The biosphere had been cut back to the Cambium, but the tree still lived. There is no need for drama beyond the facts. At the peak of the Siberian traps, ash dimmed the light, seas warmed and lost their breath, and forests thinned under acid rain and dust. Hydrogen sulfide tainted coasts and, at times, the air. The losses were global and deep. Yet, the record is also clear about what followed. A long, uneven, but real recovery, led by organisms able to endure and adapt in a changed world. In that spare beginning, one land animal stands out in the rocks. Fossil beds from this window are packed with its bones, sometimes close to 90% of the vertebrate remains. Lystrosaurus was not flashy or fast, but it was tough and adaptable, seemingly unbothered by the broken landscape. Its advantages were simple and well matched to the stress. A generalist herbivore that could feed on tough, fibrous plants in many settings, a body likely capable of burrowing or sheltering in shallow scrapes to ride out heat and drought, and a chest and airway built for efficient breathing at small size, useful in low oxygen air. In short, it did not need much. In a post-crisis world, that was a superpower, and it helped anchor the first steps of recovery. While Lystrosaurus ruled the land, the oceans rebuilt from the bottom up. Diversity had fallen to a bare minimum. Many brachiopod lines were gone. Trilobites were gone. Several ammonoid families had vanished. Reef builders had collapsed. What returned first were simple, low-diversity communities made of hardy forms. In many shallow areas, microbial mats resurfaced thick carpets of bacteria and other single-celled life that knit sediment together, cycled nutrients, and stabilized flats. This was a throwback to much earlier Earth, when mats shaped coastlines before animals learned to graze them down. Above the mats, small bivalves and gastropods crept back. In open water, a few ammonoids reappeared and began a slow radiation. Fishes persisted and then diversified, but the complex webs of the late Permian did not snap back quickly. For several million years, the sea stayed simplified and fragile, with low diversity and short food chains that could be toppled by heat spikes or renewed anoxia. On land, plants returned in patches. The lush peat swamps of the Permian gave way to sparser cover, especially in the hot, dry belts of Pangaea's interior. Lycopods and ferns held on where water lingered. Early gymnosperms, conifers, and seed ferns spread along cooler uplands and coasts. With thin plant cover, soils eroded more easily. Rivers carried heavy loads of sand and silt. Floodplains turned muddy and unstable. Yet even in this rough setting, evolution did what it always does with empty space. It experimented. The extinction had cleared many roles. New lineages could try new body plans and behaviors without being outcompeted by the old masters. Archosaurs rose into the opening. This broad group would later give us crocodiles, pterosaurs, dinosaurs, and birds. In the early Triassic, their relatives explored many designs: long-snouted, semi-aquatic hunters, armored, herbivorous forms with high backs and heavy plates, quick, upright runners built for open ground. Alongside them, the cynodonts, mammal-like synapsids with differentiated teeth and likely warm-blooded tendencies, also diversified, mostly at small sizes and in nocturnal niches. The bottleneck had been brutal, but it favored fast life cycles, broad diets, and bodies that could handle heat and dryness. With less competition, survivors could evolve quickly to fill emptied niches. The Triassic was a long lesson in cautious reinvention. The continents were still locked together as Pangaea, giving Earth a lopsided look, one giant landmass wrapped by the Panthalassic Ocean. Interiors were arid and seasonal, with blistering summers and cold winters. Coasts had more moisture and a bit more stability. That is where forests of conifers and seed ferns took hold, where insects began their recovery, and where vertebrates found the first real footholds. Phytosaurs, crocodile-like archosaurs with nostrils set near the eyes, haunted rivers and lakes. Apatosaurs, heavily armored, tank-like herbivores trundled across floodplains. Early true crocodile relatives explored both land and water. Small, shrew-sized cynodonts prowled the undergrowth, using sharp teeth to tackle insects and small vertebrates. The first true mammals likely appeared by the late Triassic, tiny, warm-blooded, nocturnal, and alert. Among the new walkers were lightly built, two-legged reptiles with long tails and upright hips, the first dinosaurs. At the start, they were not rulers. They were mid-rank runners and opportunists, slipping through shrubs and along river bars, careful to avoid the jaws of older, established archosaurs. Speed and posture gave them efficiency, but they were not yet large or dominant. For much of the Triassic, archosaurs outside the dinosaur branch held the top predator and heavy herbivore slots. Dinosaurs were one more experiment in a world still testing options. Marine life tracked a similar arc of trial and error. Ammonoids recovered in pulses, evolving new shell shapes that may have been tuned to changing waters. Bivalves and gastropods diversified across muddy shelves and delta fronts. Conodonts, tooth-bearing, eel-like swimmers that had been key players in Paleozoic seas, declined and disappeared by the end of the Triassic. Reef systems returned slowly in patchy forms, often built by sponges and early corals, but remained vulnerable to warming and anoxia events that still flared now and then. Carbonate platforms grew where chemistry allowed, then paused or collapsed when waters lost oxygen or grew too acidic. The rhythm of stress and recovery had one more hard strike left, around 201 million years ago, as the Triassic drew to a close. Fossil records, on land and at sea, show a sharp drop in diversity. Many large, non-dinosaurian archosaurs, big upright predators and armored herbivores declined or vanished. Several marine reptile groups suffered heavy losses. Insects took another hit. Plant floras shifted again. The stage cleared in some regions quickly. In others, over pulses spread across tens to hundreds of thousands of years. The driver looks familiar. Massive volcanism tied to continental breakup. As Pangaea began to rift, a vast province of magma spread along the seams of what would become the Atlantic. Geologists call it the Central Atlantic Magmatic Province, or CAMP. It poured out flood basalts across parts of what are now North America, South America, Africa, and Europe. The eruptions did not flash and fade. They came in large pulses. Each pulse sent new swells of CO2 and other gases into the air. Greenhouse forcings spiked. Temperatures rose. Short-lived sulfur aerosols may have brought brief cool snaps and acid rain between warm intervals, adding whiplash to an already stressed biosphere. In the oceans, warming and chemistry shifts again favored low oxygen. In rivers and lakes, sediment and nutrient surges followed fire and erosion on land. Under these pressures, many of the dominant Triassic archosaurs outside the dinosaur line lost ground. That loss mattered. With the older giants gone, the nimble, upright dinosaurs, already efficient walkers with light skeletons and high endurance, expanded. Herbivorous lines grew in size and variety. Predatory lines developed stronger jaws and grasping hands. In the early Jurassic, they would take center stage on land, not because they were preordained to rule, but because the deck had been reshuffled and their traits fit the new game. The early Triassic's disaster communities gave way, step by step, to more layered systems, river corridors with crocodile kin, and small mammals in the shade of conifers, dune fields crossed by two-legged tracks, coastal shelves where bivalves and ammonoids began to build numbers, open uplands where light, fast dinosaurs chased small prey between cycads and ferns. None of this happened overnight. The best estimates suggest 5 to 10 million years for the biosphere to rebuild basic diversity after the Great Dying, and longer for reefs and forests to reach pre-Permian complexity. The end Triassic shock added new delays and directed the flow of innovation. Across these swings, a pattern holds. When crises thin the field, generalists, burrowers, and small-bodied forms bridge the gap. Microbes stabilize the base. Plants return in bands along water first, then climb slopes and spread seed. Insects follow the green. Small vertebrates track the insects. Larger predators and heavy herbivores come last. Geography sets the pace. Supercontinents slow recovery inland and favor extremes. Rifting creates new coasts and climates, opening room for experiments. Volcanism, through gas and ash, pulls the strings of air and ocean. Life, built for trial and error, finds paths through. Lystrosaurus marks one such path, a compact, sturdy grazer that filled empty plains while the climate burned off its excess heat. Microbial mats mark another, a quiet carpet that held shorelines together until animals were ready to return. The earliest dinosaurs mark a third, quick, lightly built runners that waited in the wings until a final reshuffle brought them forward. The thread that connects them is not glory but function, breathing well in poor air, eating what is available, moving with little waste, reproducing fast enough to ride the swings. In the Triassic, those functions rebuilt the living world, piece by deliberate piece, until new forests, shaded floodplains, and new footsteps crossed the sand. Ocean temperatures followed suit. Weather patterns grew unstable. Some regions saw heavy, repeated rains. Others dried out for seasons at a time. Extremes sharpened. Ecosystems that had barely regained their footing after the Permian collapse were pushed into a new crisis. Heat alone stressed food webs, but the chemistry shift mattered just as much. As the atmosphere loaded with carbon dioxide, the oceans absorbed part of it. In seawater, CO2 forms, carbonic acid, lowering pH, and shifting carbonate balance. creatures that build calcium carbonate shells and skeletons. Many mollusks, corals, and plankton struggled to form and keep their hard parts in more acidic water. Growth slowed. Young stages failed more often. With fewer shell makers at the base, food chains wobbled and then broke. Marine diversity fell in pulse after pulse. The end Triassic extinction was smaller than the Great Dying, but it was still a major shock. Large reptilian competitors on land declined or vanished. Several marine reptile groups were cut back. Many amphibians disappeared from stressed lowlands and floodplains. Once more, Earth's communities were forced to reset, and this time, the survivors would inherit a world primed for a different kind of ruler. The dinosaurs were ready. When the dominant non-dinosaurian archosaurs lost ground, open roles appeared everywhere. Dinosaurs moved into them with speed. They diversified into small and large herbivores, quick-footed predators, fleet runners, and heavy browsers. The lightly built bipeds of the late Triassic began to branch toward the long-necked sauropodomorphs, the armored thyreophorans, and the sharp-toothed theropods that would rule the Jurassic. This was not a hostile takeover. It was a quiet tide. Evolutionary success often depends on being present when niches open, then having the flexibility to fill them. Dinosaurs were not magically more advanced, but they were adaptable, and they were lucky. They survived the pulses, endured the heat swings, and when the curtain rose, they were on stage. The pattern is familiar. Collapse, then radiation. Life builds, falters, and builds again, each time with a new cast and new strategies. The Triassic-Jurassic extinction followed that script. It cleared space not only for dinosaurs, but also for modern-style coral reefs, new marine hunters, and the shadowy beginnings of mammals. As the Jurassic dawned, climates warmed without the extremes of the supercontinent's harsh interiors, and the slow separation of land masses began. Plants spread in thick belts. Rivers meandered through conifer forests. On these foundations, dinosaurs did more than persist. They flourished for the next 135 million years, shaping ecosystems from canopy to ground. Right after the boundary, the atmosphere still carried traces of ash and heat from the Central Atlantic magmatic province. CO2 stayed high for a time. Ocean chemistry was not fully steady. Yet the recovery moved faster than after the Permian, because fewer systems had been pushed past their deepest thresholds. Coral communities reassembled in steppes. Reef frameworks, now dominated by scleractinian corals rather than the old Paleozoic builders, took hold in clear, shallow waters. Ammonites diversified rapidly, changing shell shapes and life habits. Marine crocodile relatives and early ichthyosaurs chased fish over continental shelves. On land, ferns and seed ferns filled open ground after fires. Conifers retook slopes and uplands as soils stabilized. Among land animals, the balance shifted. During much of the Triassic, the top roles had belonged to pseudosuchians, the crocodile-line archosaurs. Many were fast, upright hunters. Others were heavy, armored herbivores. The end Triassic shock thinned them. Dinosaurs, already present but minor, expanded to fill predator and herbivore roles. Their hip structure and pillar-like limbs made walking and running efficient. Air sacs linked to lungs likely improved breathing, a plus for active movement in warm air. Their light but strong skeletons allowed growth along many paths: speed, size, armor, or long necks. Within a few million years, dinosaur groups radiated into varied forms across floodplains, woodlands, and dune fields. Early Jurassic faunas show this speed: small, slender theropods coursed along river bars, leaving three-toed tracks in wet sand. Plate-bearing herbivores tested simple armor. Long-necked sauropodomorphs browsed higher than any competitor, turning scattered groves into dependable food. Some lineages experimented with quills and simple display structures. Others thickened tail clubs or added shoulder spines. The mix of traits tells a clear story. When competition is low and habitats are diverse, evolution explores options quickly. Meanwhile, another branch of the Triassic survivors kept to the margins. The early mammals. Descended from synapsids, they had already split from the line leading to large Triassic synapsid predators. In the early Jurassic, they were small, mostly nocturnal, and likely insect-eating. Hiding by day reduced conflicts with diurnal dinosaurs and reptile hunters. Warm-blooded metabolism let them stay active during cool nights. Fur helped hold heat. Sensitive hearing and good noses improved foraging in leaf litter. They were not failures. They were patient. Their strategy traded size and daylight for safety and persistence. Ocean stories echoed the land. Acidification spikes eased and returned in waves as volcanism pulsed and weathering drew down CO2. In that push-pull, shell-forming plankton adapted. Calcareous nanoplankton and other microfossils diversified through the early Jurassic, helping rebuild marine food webs from the base. Ammonites cycled through rapid turnovers, but maintained high diversity overall. Marine reptiles split into specialized lines fast. Tuna-shaped ichthyosaurs, long-necked plesiosaurs built for ambush, stout-bodied pliosaurs with large skulls, bony fish, refined tail shapes and jaw mechanics, expanding into reefs, lagoons, and open shelves. Geography set the rhythm. As rifts widened, new shorelines and interior seas formed. Fresh coasts meant more shallow habitats with sunlight and nutrients. Passages between basins allowed migrations and mixing, which boosts diversity. Mountain belts and rain shadows created local climates, carving out pockets for different plant communities. Where water and soil were steady, forests thickened. Where winds and drought ruled, open fern and cycad fields supported herds of small herbivores and packs of mid-sized predators. Through it all, one principle stands out. Extinctions do not just remove species, they remove constraints. When the field clears, lineages with flexible bodies, broad diets, and efficient movement expand first. Dinosaurs matched that formula at the right time. Upright gait cut energy costs. Lungs with air sacs supported higher activity. Light bones enabled growth and length without heavy penalties. Teeth and beaks adapted to many foods, from tough cycads to small running prey. Variation within clutches and fast juvenile growth likely helped populations rebound after drought or fire. The speed of diversification can tempt us to call it inevitable. It was not. Had the camp pulses been weaker, had the climate swings been milder, pseudo-Suchians might have kept the top roles longer. Had another stress favored different traits, a separate branch might have risen. What happened instead is grounded in sequence and fit. Volcanism raised CO2. Heat and acidification stressed seas and coasts. Major competitors faded. Dinosaurs already carried traits suited to the new mix of habitats. They spread and specialized. By the mid-Jurassic, the outlines of a new world were visible. River systems threaded conifer forests, fern prairies stretched between groves, sauropods grazed high foliage, stegosaurs swept low plants with beaks and ground them with cheeks and plates that may also have shed heat. Theropods ranged from fox-sized insect snatchers to fleet deer-sized hunters that tested group behavior. Along cliffs and lagoons, pterosaurs rode thermals over water made bright by plankton. Offshore, ammonites spiraled through tiers of depth, while ichthyosaurs coursed like living torpedoes. Recovery had become structure. Structure had become opportunity. Opportunity had become diversity. What tied this together was not a single champion species, but a set of working solutions in a changed climate and geography. Efficient breathing, efficient gait, modular skeletons, and flexible diets win when environments shift. Small, hidden mammals proved that quiet strategies hold value in the long game. Reef corals returned with new partners and chemistries. Plankton learned the new ocean and fed the rest. After fire and flood basalts, after acid and heat, the living world organized itself once more into layered, resilient systems. This is evolution by subtraction as much as by invention. An extinction cleared the board, and dinosaurs simply rolled the best dice. In that sense, the Jurassic felt less like a triumphal march and more like a fortunate arrangement of timing and traits. Had the volcanism that ended the Triassic not happened, pseudo-Suchians might have kept the throne. Dinosaurs might have stayed side characters in someone else's story. But Earth tilted, climates shifted, and the cards fell differently. Because of that, the age of dinosaurs began. Their rule stretched for more than 130 million years and reached every continent and climate. Polar forests with months of dim light, equatorial swamps thick with ferns, highland basins with seasonal drought. Dinosaurs adapted to them all, not just big, but efficient. Many likely had air sac-based lungs that moved air through the body the way modern birds do. Their hips and limbs set under the body let them walk and run with less wasted energy. Some lived in groups, cared for nests, or migrated. They filled ground-level grazing roles, mid-level browsing roles, sprinting predator roles, and slow, heavy herbivore roles. For a long time, that system worked. As the Triassic ended and the Jurassic began, Earth seemed to take a steadier breath. The noise of rifting and flood basalts eased. Rainfall became more regular in many regions. CO2 stayed high but steadier, which meant warm, humid conditions that favored plants. Sea levels rose, flooding edges of continents and creating shallow seas rich in nutrients and light. In that calmer frame, life expanded in size and scope. Landscapes were green without flowers. Ferns, cycads, seed ferns, and conifers cast layered shade. No bees yet, no blossoms, but thick mats of fronds and scaly cones made dependable food for large herbivores. Into this buffet stepped the sauropods. Long necks like cranes, tails like counterweights, torso barrels, carried on pillar legs. These giants lifted their heads into conifer canopies and swept wide arcs of foliage. Diplodocids stretched over 20 meters from snout to tail tip. Brachiosaur-like forms stood tall, forelimbs longer than hind limbs, reaching higher than rivals could. How did they get so big? Partly physiology, high-efficiency lungs, fast growth, and bones full of air spaces that saved weight. Partly ecology, vast plant production, few competing mega herbivores, and warm climates that kept growing seasons long. Predators adjusted to match. Theropods like Allosaurus were not the heaviest of all time, but they were tuned for the Jurassic mix. Strong hind limbs, flexible necks, hands for grasping, serrated teeth for slicing. They likely hunted the young or weak in sauropod herds, or focused on medium-sized ornithischians when giants were too risky. Packs pairs, or solitary ambushes, all would have worked in different habitats. The seas wrote a parallel story with different actors. Reptiles took marine crowns. Ichthyosaurs, shaped like modern tuna or dolphins, used crescent tails and stiff bodies to move fast. They bore live young, had large eyes for low light, and ranged from small fish chasers to multi-ton hunters. Plesiosaurs split into long-necked forms with small heads and short-necked big-skulled forms with crushing bites. Sharks diversified. Bony fish refined fins and jaws. Ammonites, those coiled shelled cephalopods, pulsed through boom and bust cycles, but stayed abundant and varied, becoming key prey for reptiles and fish. Reefs returned in patches, made by scleractinian corals and sponges, where water stayed clear and warm. Overhead, pterosaurs opened a new frontier. Early forms were small, light, and agile over rivers and coasts. Later lines would reach huge wingspans. They were not dinosaurs but close relatives, and their flight added a high layer to food webs, scavenging, insect hunting, fish snatching. In the leaf litter, early mammals kept to the night. They were small, warm-blooded, lightly furred, with sharper hearing and better smell than many reptiles. They ate insects, seeds, or small vertebrates and hid from daytime hunters. By staying small and nocturnal, they avoided direct competition, honed brains and senses, and waited. The Jurassic was balanced, but never still. Forests burned in some seasons, then regrew. Rivers shifted course, lakes dried and refilled. Volcanoes still erupted on smaller scales. Yet the overall pattern held. Steady warmth, high plant growth, wide, shallow seas, and expanding coastlines. Geography slowly changed as the supercontinent rifted. New ocean basins formed. Islands and peninsulas diversified climates and isolated populations, encouraging speciation. By the late Cretaceous, the world looked different again. Flowering plants appeared and spread, adding new foods, scents, and colors. Insects followed, including pollinators. Many herbivorous dinosaurs adapted to tougher, more varied vegetation, developing complex jaws and dental batteries that could grind. Herds of hadrosaurs and ceratopsians worked floodplains. Ankylosaurs added armor and tail clubs. Tyrannosaurs refined strength and bite force. Long-necked sauropods persisted in some regions, especially in the south. Pterosaurs shared the air with true birds, which evolved from small theropods with feathers already serving for insulation and display. Then came the event that reset the stage again. About 66 million years ago, an asteroid, roughly 10 kilometers wide, struck the Yucatan Peninsula at around 20 kilometers per second. The impact formed the Chicxulub crater, more than 180 kilometers across, with a central ring uplift and melted rock pooled in a vast basin. Shockwaves, fractured crust, rock turned to vapor. Ejecta shot above the atmosphere and rained back down as glassy spherules and dust. Within minutes to hours, re-entering debris heated the upper air enough to start fires across continents. Tsunamis raced outward, scouring coasts and leaving sediment layers we can still trace. The force did not end with heat and waves. The target rocks were rich in sulfur. Vaporized sulfates, along with soot from global fires, lofted into the stratosphere and spread worldwide. Sunlight dimmed. Photosynthesis stalled. Temperatures fell quickly for months to years, a sharp chill on top of local heat pulses. In the oceans, the plankton that formed the base of food webs crashed. On land, leafy forests browned and fell silent. With producers failing, Herbivores starved, then carnivores did. It was not instant everywhere, but within a short span, ecosystems failed in linked cascades. Evidence of the event sits in a thin layer of clay found around the world. It is enriched in iridium, rare in Earth's crust, but common in meteorites. It holds shocked quartz grains, tiny spherules of melted rock and soot. Drill cores from the crater match the timing. The signal is global and sharp, an unmistakable boundary. Losses were heavy. Non-avian dinosaurs disappeared. Pterosaurs went with them. Many marine reptiles, including mosasaurs and plesiosaurs, vanished. Ammonites ended after 500 million years of cephalopod history. Reefs suffered. On land, some plant groups dipped, but rebounded. Fern spores often surge right above the boundary, a fern spike that marks quick colonizers of burned ground. Not all lineages fell. Crocodilians lived through, likely aided by semi-aquatic habits, slow metabolisms, and tolerance for long fasting. Turtles, with broad diets and protective shells, persisted in rivers and coasts. Many small mammals survived, sheltered in burrows and crevices, eating seeds, insects, and carrion. Birds, the only living dinosaurs, made it through in a few lines, particularly those with ground-feeding habits and beaks suited to seeds and detritus when fresh leaves were scarce. In the sea, some fishes and invertebrates endured in deep or high latitude refuges, where the light drop was less absolute. After the dust settled enough to let light through, recovery followed the old order. Microbes and ferns first, then shrubs and trees, insects back with the green, small vertebrates following food and shelter. In the oceans, tiny calcifying plankton re-evolved shapes that handled the changed chemistry. Foraminifera, coccolithophores, and diatoms took turns at the base. Coral reefs took longer, but when stabilized climates returned, they rebuilt with new coral and algae partnerships. Mammals, freed from the shadow of giant diurnal reptiles, diversified quickly in the Paleocene and Eocene. Some ate insects, others took to seeds and fruit as flowering plants spread. Hoofed mammals developed larger bodies and complex teeth. Primates refined grasping hands and forward-facing eyes in forest canopies. Whales evolved from shore-running artiodactyls into open ocean swimmers within a few tens of millions of years. Bats took to powered flight. Rodents and lagomorphs filled small herbivore roles. Carnivores sharpened teeth and coordination. The age of mammals was not a single surge. It was many radiations paced by climate swings, tectonics, and plant evolution. But the opening came from the reset. Birds radiated too. Ground-living seed-eaters branched into waders, divers, raptors, and songbirds. Feathers, first used for warmth and display, carried lineages into new niches. Beaks specialized. Sieves, drills, hooks, and chisels. Flight traded body mass for range and speed, linking habitats and allowing quick recolonization after local shocks. Even in this post-impact world, volcanoes played roles. The Deccan Traps in India erupted around the same time as the impact. Their gases likely pushed the climate before and after the strike. But the sharp, global, synchronous markers, the iridium layer, the spherules, the shocked minerals, and the crater itself tie the main kill pulse to the asteroid. Volcanism may have stressed ecosystems and shaped the longer recovery curve. The impact delivered the decisive blow. What followed, again, was evolution by subtraction and opportunity. Remove apex diurnal reptile predators and megaherbivores. The night opens for small, warm-blooded forms. Remove ammonites. Other cephalopods adjust, and fish take broader roles. Thin reef builders. Survivor corals partner with symbionts that handle warmer, variable water. Each loss changed the playing field. Each survivor brought tools that fit the new rules. Across all these chapters, the Ordovician chill, the Devonian drawn-out decline, the Permian furnace, the Triassic-Jurassic reshuffle, and the Cretaceous impact, the pattern repeats. Earth's systems couple climate, chemistry, and geography tightly. When pushed past thresholds, they tip. Extinctions do not only cut branches, they change the shape of the tree. The next canopy grows from whatever twig remains, not from what was once ideal. Generalists, burrowers, small-bodied forms, flexible breathers, and opportunistic feeders carry the torch through the dark. Once stability returns, specialization builds again. Long necks, armor plates, complex jaws, soaring wings, echolocation clicks, baleen sieves. The Jurassic stands out as a long interval when conditions aligned for size and abundance. Warm air, high CO2, steady rains, high sea levels, and splitting continents set tables that giants could use. Sauropods reached heights and masses that land animals have not matched since. Theropods tuned speed and bite to fit that world. Pterosaurs exploited uplift along cliffs and thermals over warm seas. Mammals refined senses in shade. None of it was guaranteed. It followed from a prior clearing and a particular climate-continent mix. The Cretaceous shows how a single external strike can reverse that balance quickly. Heat, then darkness, wildfire and winter, acid rain and chilled seas. Producers fail, consumers fail. The map of life redraws. The survivors were not better in some universal sense. They were better for a cold, dark, ash-laden world and the variable centuries that followed. Their descendants, mammals and birds especially, built the next complexity. We can point to the signs in rocks with simple tools. A black shale for anoxia, a gap where coals should be for forest loss, rust-red beds for arid pulses, spherules in a clay seam for impact fallout, iridium peaks for extraterrestrial metal, shocked quartz for sudden pressure. We can trace bones and shells across layers, many kinds, then few, then new kinds. We can read the chemistry of teeth and the growth rings of bones to see seasonality and stress. Layer by layer, the record writes the same basic lesson in different scripts. When the rules change, life changes with them. Not all at once, not evenly, but firmly. So the Jurassic triumph was a moment of fit between life's tools and Earth's settings. The end-Triassic volcanism did not make dinosaurs superior. It removed competitors and made a world their bodies could use to full effect. The Cretaceous impact did not make mammals better. It made them relevant and safe enough to expand. If the dice had rolled differently, we would tell different names and shapes. The logic would be the same. Subtraction, then invention, stress, then structure, a cleared board, then a new game with familiar rules: breathe, eat, move, grow, reproduce, played by different pieces on a different map. None of this needs grand language. It needs clear steps. Flood basalts heat air and acidify rain. Oceans lose oxygen. Microbes switch pathways, gases hurt ozone, UV rises, plants thin, soils erode, rivers load the shelves, dead zones widen, reefs fail, strong generalists bridge the gap, asteroids strike, dust and sulfate darken skies, photosynthesis stops, food webs crack, small, hidden, flexible forms survive. When light and warmth return within a tolerable range, plants sprout, insects buzz, fish school, reptiles bask, mammals skitter, birds flit. Layer by layer, diversity thickens until the next stress. In that sequence, the Jurassic was a high plateau of green and muscle and air. Sauropods reached, theropods chased, pterosaurs soared, mammals waited. The Cretaceous impact ended that plateau with a clean line. The Paleogene wrote a different table of contents. Forests with fruit, herds with teeth that grow all life, seas with whales that sing. We inherit that table of contents. Every robin and eagle comes from birds that outlasted ash. Every mouse and human comes from mammals that hid and endured, then explored new diets and daylights. The same physics that once favored long necks and hollow bones now favors big brains, nimble hands, and social learning. The rule has not changed. When the world clears and resets, those who can breathe well, eat what is on offer, move with little waste, and raise young through swings will shape what comes next. For animals, especially those tied to complex food webs or that needed a lot of energy to grow cold and dark, were brutal. Herbivores found no new leaves or cones. Carnivores found fewer bodies to hunt. In the sea, filter feeders starved as plankton failed. Reefs sensitive to temperature and chemistry lost their partners and dimmed to skeletal frames. Ecosystems that had taken tens of millions of years to assemble came apart in layers. It is tempting to imagine a single instant of doom, but the impact was only the opening strike. What followed was a long, linked failure of systems. Light loss, plant loss, plankton loss, oxygen stress, food web collapse. It was not one moment, but many. Survival tilted toward the small and the flexible. Mammals had already lived in the margins for a long time. They nested in burrows and crevices, hunted insects, cached seeds, and could switch foods when one ran short. Many likely sheltered underground during the first heat pulse and the months of choking air. Small bodies demanded less energy. Some species could enter torpor or hibernation, slowing their needs when the world offered little. Warm-blooded bodies kept muscles and brains working during a fast chill. When nights lengthened and days stayed cold, that mattered. Birds show the same pattern. Not all avian dinosaurs made it. Large, specialized birds of the late Cretaceous disappeared with their kin. The survivors were small, ground-dwelling, and generalist. Seeds, detritus, invertebrates, foods that persist through hard seasons kept them going. Feathers trapped heat. Wings gave range to search for new pockets of shelter and food. From those soot-dusted survivors came the lines that would later branch into water divers, desert runners, forest singers, and city foragers. Oceans reset from the base up, with photosynthetic plankton knocked back and many top reptiles gone. The first steps were chemical. Dust settled, light returned, carbonate balance slowly improved. Some sharks and bony fish persisted and spread. Deep-sea communities, buffered from surface shocks, fared better than sunlit waters. In the photic zone, tiny calcifiers and silica users rebuilt first coccolithophores, diatoms, and small foraminifera. Reefs took far longer. When they did return, it was with corals and symbionts tuned to the new seas. On land, plants staged a layered comeback. Spore formers like ferns often show a brief surge just above the boundary, taking over burned ground. Seed plants followed as soils stabilized. Conifers, then broad-leaved flowering plants, expanding into light gaps. Flowering plants were not new, but with competitors thinned, they diversified rapidly. Flowers brought new signals and rewards. Fruits and nuts offered dense packets of energy. Grasses would later remake open landscapes, but even early on, angiosperms began reshaping forests with faster growth and flexible strategies. Mammals moved into the space that opened. The first Paleocene faunas feature modest, generalized forms: insect eaters, seed and fruit browsers, small omnivores. Marsupials and placentals both spread, while monotremes held on in limited ranges. Placentals bearing young that develop longer before birth radiated especially fast. Within a few million years, body sizes began to climb. In forests that returned thick and dim, primates tested grasping hands, forward-facing eyes, and depth vision for living in branches. Hoofed mammals split into odd-toed and even-toed lines, refining teeth for tough plants and longer legs for distance. Early carnivores sharpened slicing teeth and senses. Rodents evolved chisel-like incisors and fast breeding, becoming key seed movers and prey. The oceans saw their own new giants, but only after groundwork was laid. Artiodactyl relatives along warm coasts began wading, then swimming. Limbs flattened, nostrils shifted. Bones gained density for ballast. Over the Eocene, those shorerunners became the first whales, streamlined, tail-driven, fully aquatic. Bats took to the air around the same time, mastering powered flight with thin skin membranes and precise echolocation. Flight at night let them harvest insects in a niche with little competition. Climate nudged these radiations. The early Paleocene was cool relative to the Cretaceous. Forests grew in broad belts. Then came a sharp, short warming pulse, the Paleocene-Eocene thermal maximum, driven by a rapid carbon injection. Temperatures rose, rainfall patterns shifted, tropical and subtropical plants and animals expanded poleward, plankton communities rearranged, but food webs held. Warmth opened corridors for dispersal. Lineages mixed and diversified. When temperatures later eased, some groups retracted, others adapted in place. As flowering plants expanded, coevolution tightened. Insects evolved mouthparts to sip nectar and carry pollen. Plants tuned colors, scents, and shapes to match their helpers. Fruits changed size and packaging to recruit mammals and birds as seed spreaders. Teeth and guts mirrored diets, grinding ridges for grass, shearing blades for meat, mixed dentitions for omnivory. Brains and social behavior grew where problem-solving paid a trend visible in carnivores, primates, and some ungulates. Recovery had rules seen in earlier chapters. Generalists lead. Small bodies bridge the gap. Diversity returns bottom up. Microbes, then plants and plankton, then insects and small vertebrates, and only later big, specialized forms. Geography steers pace and options. In the Paleogene, continents drifted apart farther, carving new coasts, currents, and climates. The North Atlantic opened wider. The Tethys narrowed. Ocean circulation patterns shifted, creating upwelling zones rich in nutrients and quiet basins that stored carbon. Mountains rose and cast rain shadows, setting dry grasslands and wet forests side by side. That patchwork multiplied niches. Birds kept pace with the plants. Seed eaters diversified with fruiting trees and grasses. Shorebirds refined beaks into probes, sieves, and picks. Raptors sharpened talons and vision for open country. Penguins adapted wings into flippers and moved hunting to cold seas. Songbirds learned to use voice as a tool for territory, mates, and social ties riding the spread of complex forests. Not all lines prospered. Some large Paleocene herbivores failed when climates swung. Some early carnivores were replaced by more efficient hunters. Reefs paused during chemistry bumps and storms. But compared with the wrenching resets of older mass extinctions, the post-KPG world held its footing. CO2 fell from the impact spike over time. Light returned. Forests matured. Rivers found stable courses. The fabric of life thickened and reinforced. The key point is simple. The survivors of the boundary were not better in a timeless sense. They were better matched to a dark, cold interval and the mixed climates that followed. Small, warm-blooded bodies that hide, beaks that crack seeds, wings that carry refugees to fresh ground, teeth that handle many foods, wombs and nests that protect young during swings. These are tools that win in resets. Once the sun returned and plants spread, those same tools supported rapid innovation. From that platform, the outlines of the modern world took shape. Forest canopies with primates and birds, open plains with running herbivores and pursuit predators, coasts with diving birds and seals, oceans with schools of fish, pods of whales, and reefs humming with partnerships. The path passed through ash and chill, but the steps followed the same logic seen after earlier crises. Prune, persist, rebuild, diversify. The difference this time is that one of the small, warm-blooded lines would eventually learn to read the rocks and tell the story. Lineages branched into many forms. Some moved into trees and developed grasping hands and forward-facing eyes, the first primates. Others learned speed and endurance on spreading grasslands, with longer legs and teeth built to grind. A few became expert diggers that fed underground. Others turned into swimmers that pushed back to the sea. Whales built tail-driven bodies and echolocation. Bats mastered powered flight at night. Elephants grew trunks and tusks for touch, smell, and defense. Cats, dogs, bears, rodents, and apes each found workable paths through shifting climates and changing landscapes. It wasn't chaos. It was competition for open seats after a mass reset. Traits that helped in hard times live birth. Fur for insulation. Warm-blooded metabolism gave mammals steady power. So did larger brains, which allowed flexible behavior when conditions changed faster than bodies could. From this broad experiment came us. Humans descend from primates that once lived in Eocene forests, moving branch to branch under thick canopies. Our thumbs, social bonds, language, and large brains are the outcomes of many small bets placed over millions of years. We are here not in spite of catastrophe, but because the living world reformed after it. That is a humbling idea. Your ability to lie back and listen to this, to think about deep time at all, rests on 5 great collapses that came before. Each event reshaped the planet's living map. The Ordovician Silurian crisis drained shallow seas and chilled the oceans. Many early marine groups vanished. Survivors rebuilt food webs in colder, lower seas. The Devonian decline unfolded in pulses as plants pulled CO2 from the air, and rivers sent nutrients to coasts, driving oxygen loss in the water. Reefs faltered, some fishes, and the first tetrapods edged toward land. The Permian-Triassic Great Dying nearly reset everything. Flood basalts warmed the air, oceans lost breath, and toxic gases rose. Few lineages bridged that gap. Those that did set the base for the Triassic world. At the Triassic-Jurassic boundary, more volcanism raised CO2 again. Many crocodile-line archosaurs fell. Dinosaurs expanded into open rolls. And at the end of the Cretaceous, the Chicxulub impact ended non-avian dinosaurs and opened the Paleogene to birds and mammals. Every time, the pattern held. Remove the old structure, and new forms spread. Fish with jaws, land-walking vertebrates, flowering plants, birds, whales, primates. Each wave followed an earlier loss. That does not make loss good. It makes the record plain. When space opens, life fills it with what remains, not with what was. The Paleogene and Neogene built the world's modern outlines. As continents drifted, climates changed by steps. Mountain chains rose and cast rain shadows. Currents shifted around new seaways. Grasslands expanded. With them came grazers that could wear down and replace teeth, and runners that saved energy with long strides. Predators adjusted with better noses, keener eyes, and coordinated hunts. In forests, fruiting trees and vines recruited birds and primates as seed spreaders. Cooperation, communication, and memory mattered more where groups raised young and defended territories. Brains grew where planning paid off. Whales show how fast large-scale change can work when the path is open. Early Eocene shorerunners waded and swam. Their hips detached from the spine, their limbs flattened, their tails took over. In a few million years, they were fully marine, with sonar to see in dark water. Bats show a different solution. Take to the night sky and use sound to map insects. Both lineages built new ways to live from older parts. Limbs, ears, lungs retuned for new jobs. Birds diversified alongside flowering plants. Seed eaters learned to crack, grind, or swallow whole. Waders tuned bills for mud probing or fish spearing. Raptors soared over open country that did not exist before grasses. Penguins turned wings into flippers and hunted in cold seas. Many groups added learned songs and social calls, a flexible layer on top of instinct. That mix built body. Learned behavior proved useful in changeable climates. Humans appear very late in this record. Bipedal apes learned to walk long distances, split tasks, and share food. Hands that could grip and pivot handled tools with growing skill. Fire, storage, and language widened the range of places our ancestors could live. Over time, small bands became villages and cities. With success came reach. Forests cut to fields, rivers dammed, animals bred or hunted out. In a few centuries, the scale of change grew large enough to alter air and sea. That is where we are now. Scientists see warning signs in today's trends. Habitats shrink and fragment. Oceans grow warmer and more acidic. Reefs bleach. Invasive species spread. Wild populations thin. Extinction rates rise above background levels. Some call this the early phase of a sixth mass extinction, driven by one species rather than by volcanoes or impacts. The comparison is not exact. We still have great forests, vibrant reefs, and vast herds and flocks in some places, but the direction is clear enough to ask for care. The deep past is not only a list of losses, it is also a guide to resilience. Generalists bridge collapses. Diversity returns from the bottom up. Microbes, plants and plankton, insects, small vertebrates, and later, large specialists. Complex partnerships, like coral algae symbiosis or pollinator flower pairs, are powerful but fragile. Geography sets the pace. Many small, connected habitats help recovery. Broad, harsh interiors slow it. If we want living systems to hold, we can keep those lessons in mind. Protect varied habitats, connect them, lower the shocks we add, let rivers, coasts, and soils do their quiet work. Remember too that the present holds old threads. Horseshoe crabs still patrol beaches with a design older than dinosaurs. Ginkgo trees grow leaves, much like those that once shaded Jurassic valleys. Lungfish rest in mud, living links to ancient coastlines. And in our own genes live traces of small mammals that slept through dark winters and woke when the light returned. The line from them to us was not guaranteed. It bent through chance and pressure and long stretches of ordinary life. So the 5 near endings we followed are not only disasters, they are pivots. The Ordovician chill opened paths for new marine communities. The Devonian pulses nudged fins toward limbs and forests toward new roles. The Permian furnace rewired air and ocean and forced a lean restart. The Triassic reshuffle set dinosaurs on their long run. The Cretaceous impact cleared daylight for birds and mammals. Without those turns, our branch would likely not exist. That is not a celebration of loss. It is an acknowledgement that we live in the wake of it. What we do next will decide how much of today's variety passes through our own tight place in time. We can slow the carbon we add. We can leave room for migration as climates shift. We can spare old-growth forests, seed banks, and reefs, because recovery is slower without them. We can learn from places that hold, mangroves that soften storms, wetlands that filter floods, prairies that store carbon in deep roots. The past says that life will return after shocks. It does not promise that our favorites, or our needs, will be among what returns if we push too hard. Still, resilience is real. After every dark interval, ferns unfurled. After every low, small bodies found food. After every silence, songs returned. If we keep more of the green and blue in place, more canopy, more reef, more cold currents and clean rivers, we leave wider paths for that return and more room for us inside it.